Chapter 1. The Beginnings of Mathematics in the Stone Age. The history of mathematics goes back further than many realize. Long before humans developed writing, before there were cities, temples, or organized states, there was already a need for counting, measuring, and comparing. Mathematics in its most elementary form arose from the need to organize life in an uncertain environment. As early as the Stone Age, tens of thousands of years before our era, people began to recognize patterns, use numbers, and develop symbols for quantities. Archaeological finds prove that people used primitive counting methods as early as about 35,000 years ago. A well-known example is the so-called Ishango bone, which was found on the banks of the Nile and is estimated to be around 20,000 years old. There are notches on this bone, which were apparently not carved by chance. Some scientists interpret them as records of number sequences or even as indications of a simple number system. Whether the Stone Age people already represented mathematical operations such as addition or subtraction here remains controversial, but it is clear that they had a need to record and record quantities. Counting was probably the first mathematical act ever. Hunters and gatherers had to count their prey, they had to know how many animals they had killed or how many members their group had. Mothers may have counted their children to make sure none were missing. To keep these amounts in mind, they used their fingers as a natural tool. The human body was the first computing apparatus. 10 fingers led to the emergence of the decimal system, which later became established in many cultures. Other groups followed the lunar cycle or used bones and sticks to mark counts. In addition to counting, measuring also played an important role early on. Even simple huts or tools required a feeling for lengths and proportions. Anyone who wanted to make a spear had to know that it had to have a certain length so that it remained stable in the throw. Anyone who sewed a hide for protection had to be able to estimate roughly how big it should be. Such practical experience led to a rudimentary understanding of geometry long before the term even existed. Timekeeping was also of central importance in early history. People observed the change of the seasons, the phases of the moon, and the course of the sun. They needed to know when was the best time to hunt, when certain plants bore fruit, or when winter was approaching. Looking at the sky led to an early kind of mathematics because people began to recognize cycles, note patterns, and perhaps even dare to make their first predictions. The combination of astronomy and mathematics was to accompany mankind into modern times. The emergence of mathematics was thus closely linked to the practical needs of survival. It was not about abstract theories or proofs, but about counting, ordering, and structuring the world. In the process, the ability to recognize and transmit patterns also developed. A simple example is the concept of repetition. 2 stones, 2 animals, 2 people. The same structure appeared everywhere. The realization that this duality existed independently of the object was a first step towards abstract thinking. As the complexity of human societies increased, so did the need for mathematics. As groups grew larger, methods were needed to distribute food or manage supplies. Perhaps there were already primitive forms of barter, in which quantities were weighed against each other. 3 skins against 5 tools, or a certain amount of berries against a piece of meat. Such actions required not only a sense of quantities, but of equality and proportion. This is where the roots of arithmetic lie, even if the people of that time did not yet know numbers in the modern sense. Stone Age mathematics was not written knowledge, but a cultural heritage that was passed on orally and through actions. Children learned to count by herding animals or collecting food with their parents. Pattern recognition was trained in everyday life when interpreting tracks in the snow or looking at the starry sky. With every new problem that nature posed, people developed new mathematical tools, even if they weren't aware of it. What is particularly fascinating is that even in this early phase, a certain abstraction is already recognizable. The Ishango bone, for example, shows not only simple strokes, but groupings that indicate conscious order. Some series can be interpreted as duplications or as indications of prime numbers. If this is true, then 20,000 years ago, people had already begun to think about numbers, not just concrete quantities. Other finds, such as the Lumbombo bone from South Africa, also point to similar practices. The beginnings of mathematics were therefore inconspicuous but decisive. They made the difference between instinct and conscious action, between mere survival and planned design. Mathematics arose from the need to order the world, to make it comprehensible, and to shape the future to a certain extent predictable. Without these early steps, there would have been no pyramids, no calendars, no algebra, no computers. The Stone Age people, who carved notches in bones or watched the moon in the sky, laid the foundation for a development that continues to this day. Their counting stones and notches may seem primitive, but they were the first expression of a way of thinking that distinguishes humanity from all other living beings. The ability to grasp the world in numbers and structures and to gain knowledge from these patterns.
Chapter 2. Mathematics in Mesopotamia. Cuneiform, clay tablets, and the sexagesimal system. While in the Stone Age, the beginnings of mathematics were mainly based on practical experience, it reached a completely new level with the first advanced civilizations. Nowhere is this transition more evident than in Mesopotamia, the land between the rivers, Euphrates and Tigris. This is where the first cities, states, and written cultures emerged around 5,000 years ago, and with them a mathematical system that formed the basis for many later developments. The Sumerians, who are considered the first advanced civilization in Mesopotamia, developed a script that was not only used for religious or literary texts, but also for administration and trade. Cuneiform writing on clay tablets was a means of recording tributes, supplies, or trade transactions. Mathematics thus moved out of the world of mere counting and became a tool of state organization. Anyone who wanted to measure fields, calculate grain stocks, or manage workers needed clear rules for numbers and arithmetic operations. A special feature of Mesopotamian mathematics was the sexagesimal system, that is, a number system to base 60. This system was extremely flexible because 60 has many divisors: 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made it very easy to represent fractions. While we are used to the decimal system based on the number 10 today, the Babylonians used their system so consistently that we can still find traces of it today. An hour has 60 minutes, a circle 360 degrees, inheritances from the mathematics of Mesopotamia. The cuneiform tablets that archaeologists have found in large numbers impressively show how versatile this mathematics was. There were boards on which multiplication tables were entered so that students could learn them by heart. Others included tasks for calculating the area of fields or calculating structures. Clay tablets containing quadratic equations are particularly noteworthy. Some of these tasks were formulated in the form of small word problems, such as, a square and its side add up to 45. Such examples show that the Babylonians were already solving algebraic problems long before the term algebra existed. The mathematics of Mesopotamia also played a central role in astronomy. The Babylonians were skillful observers of the heavens and developed a highly sophisticated calendar based on calculations. They were able to predict lunar and solar eclipses and record the movements of planets in tables. These observations were not only of scientific interest, but also important for religion and rule. Kings based their power on the interpretation of celestial signs, and priests used astronomical data to establish rituals. The practical importance of mathematics is also evident in architecture and construction. The huge ziggurats, the stepped temples of Mesopotamia, required precise planning and calculation. Field surveying was necessary to distribute land and set taxes. In all these areas, a mathematics developed that was closely linked to the needs of society. It was not an abstract game, but a tool that ensured the functioning of the early states. A fascinating example of the sophistication of Babylonian mathematics is the famous Plimpton 322 tablet, discovered in the early 20th century. It contains a table with figures that seem puzzling at first glance. But researchers realized that it was a list of so-called Pythagorean triples, sets of numbers that satisfy the Pythagorean theorem. This tablet was created about 1,000 years before Pythagoras and shows that the Babylonians had a deep understanding of mathematical relationships long before the Greeks. The way the Babylonians dealt with numbers is also remarkable. They didn't know zero in the modern sense, but they used placeholders to mark the positions of numbers in their place value system. In doing so, they laid the foundation for later developments, even if they didn't take the step to abstract zero. However, their system was so efficient that it lasted for centuries and was adopted by other cultures. The mathematics of Mesopotamia was in many ways a mathematics of practice, but it already contained many elements that later became the foundations of science. It showed that numbers not only counted for concrete things, but could express abstract relations. Whether in the calculation of areas, in the solution of equations, or in the prediction of celestial movements, everywhere it served to grasp the world in structures and rules. In addition, it had a strong didactic component. In the scribe schools, pupils were systematically taught mathematics. They learned tables, calculation methods, and problem solving. Mathematics became a part of the educated class, a knowledge that was closely linked to the administration and power of the state. Without mathematics, the vast network of taxes, building projects, and astronomical calculations that determined Mesopotamian life would not have been conceivable. When we look back at Mesopotamia today, we see a culture that gave mathematics a whole new dimension. Simple notches on bones became complex systems, counting animals became the calculation of stellar movements. The invention of the sexagesimal system and the written fixation of mathematical procedures made this culture a cornerstone of the history of mathematics. Many concepts that were developed at that time live on to this day, be it in a circle with its 360 degrees or in the clock that shows us the time in steps of 60. The mathematics of Mesopotamia was thus not only a tool of administration, but also an expression of human striving to understand and order the world. It laid a foundation on which later cultures could build, and it shows how closely practical necessity and intellectual curiosity were linked.
Chapter 3: Egyptian Mathematics, Pyramids, Nile Flood, and Practical Arithmetic. While cuneiform writing and the sexagesimal system shaped mathematics in Mesopotamia, a very special tradition developed in Egypt at the same time. Here, too, the focus was not on abstract reflection, but on solving practical problems. Egyptian mathematics was closely linked to life on the Nile, with agriculture, architecture, and administration. It served to ensure survival in a unique but challenging environment, and at the same time to erect monumental structures such as the pyramids, which still bear witness to this mathematical art today. The Nile Valley was the heart of Egypt. Every year, the river overflowed its banks, leaving fertile mud on which agriculture flourished. But these floods also changed the fields, erased borders, and made it necessary to resurvey land. This is where Egyptian mathematics began. Surveyors used ropes to move through the fields to determine areas, calculate taxes, and record ownership. Probably, our word geometry today is derived from this land measure. The Egyptians used a number system based on the number 10. They wrote their numbers in hieroglyphics. A line meant 1, a horseshoe 10, a spiral 100, a lotus 1,000, and so on. The system was additive. You simply put the symbols together.
So it was clear but not very efficient for large calculations. Nevertheless, it was enough to cope with everyday tasks such as addition, subtraction, multiplication, and division. The two most important sources of Egyptian mathematics are famous: the Rhind papyrus and the Moscow papyrus, both around 3,800 years old. They contain hundreds of problems and solutions that served as teaching material for students and writers. The tasks range from fractions to area and volume calculations to equations. The Rhind papyrus even begins with a kind of preface, in which the writer emphasizes that it is an exact science, an indication that mathematics was considered not only a craft but a serious discipline in Middle Kingdom Egypt. A special feature of Egyptian mathematics was the handling of fractions. They mainly used stem fractions, i.e., fractions with the numerator 1, for example, 1/2, 1/3, 1/4. All other fractions were represented by decomposition into trunk fractions. For example, the Egyptians wrote 2/3 as 1/2 plus 1/6. The Rhind papyrus contains long tables in which such decompositions are systematically listed. This procedure may seem cumbersome, but it was surprisingly effective and shows the practical inventiveness of the Egyptian scribes. Geometry also played an important role. The Egyptians were able to calculate areas of triangles, rectangles, and circles. For the circle, they used an approximation that was surprisingly close to our current value for pi. A well-known formula of the Rhind papyrus equates the area of a circle with the area of a square whose side length is 8/9 of the diameter. If you convert that, you get a pi value of about 3.16, a remarkable approximation for a culture that knew no abstract symbols for irrational numbers. Even more impressive is the application of this geometry in construction. The pyramids of Giza, built around 2600 BC, are not only masterpieces of architecture, but also of mathematics. The precision with which their sides were aligned and their angles determined indicates that the builders had sophisticated calculation methods. They knew the concept of proportions and used ropes to measure angles, a precursor to Pythagoras' theorem, which they knew in practical form. Volume calculations were also part of the repertoire of Egyptian mathematicians. The Moscow papyrus, for example, contains a problem that calculates the volume of a pyramid. Other tasks deal with the filling quantity of silos or jugs, important for managing stocks. These examples show how closely mathematics and everyday life were connected. In addition to agriculture and construction, mathematics also served administration. Taxes had to be calculated, workers organized, inventories recorded. The Egyptian empire was highly centralized, and the bureaucracy needed reliable figures. Mathematics was therefore a tool of power. Scribes who mastered this art formed their own elite, which was closely linked to the pharaohs. The connection between mathematics and religion is also interesting. The Nile, the sun, and the stars played a central role in the beliefs of the Egyptians, and their observation required mathematical methods. The Egyptian calendar, one of the most accurate in antiquity, was based on the observation of the star Sirius and the solar years. It divided the year into 365 days and thus came surprisingly close to our modern calendar. Without this mathematical basis, the religious festivals, which were closely linked to the rhythm of nature, would not have been conceivable. Egyptian mathematics differs significantly from the Greek mathematics that was to follow later, in one respect. It was hardly theoretical, but almost exclusively practical. It was not about providing evidence or deriving general sentences, but about solving concrete problems. But it was precisely in this practice that her strength lay. It made it possible to build monuments, administer a vast empire, and secure agriculture, which guaranteed survival on the Nile. If we look at the mathematics of the Egyptians today, we see a culture that developed a science out of the challenges of its environment. They had to understand the Nile, they had to survey land and calculate supplies, and they did so with a precision that went far beyond mere estimation. Even though their methods were often based on approximations, they laid the foundation for many concepts that were later developed further in mathematics.
The pyramids, the calendars, the papyrus scrolls, they are all testimonies to a mathematics that was not anchored in books or theories, but in the world itself. The Egyptians made mathematics a tool with which they tamed the rhythm of nature and placed their civilization on a stable foundation.
Chapter 4. The Mathematics of the Indus Culture and Early Asian Contributions. While Mesopotamia and Egypt are considered the best-known cradles of early mathematics, another advanced civilization should not be overlooked, the Indus culture, which flourished between about 2600 and 1900 BC in what is now Pakistan and northwestern India. Their cities, including Harappa and Mohenjo-Daro, show an amazing planning that would hardly have been conceivable without mathematical knowledge. Although their characters have not been fully deciphered to this day, archaeological finds indicate that highly developed mathematical thinking also existed here. The cities of the Indus culture impress with their clear structure. Streets ran in a checkerboard pattern, houses had standardized dimensions, and even bricks were made according to fixed proportions. This uniformity suggests that there was a system of weights and measures controlled by a central authority. In fact, numerous weight stones have been discovered that seem to be ordered according to a decimal system. Some finds suggest that the Indus culture achieved an accuracy of measurements that was unique in antiquity. Water management is particularly striking. In Mohenjo-Daro, there were elaborate canal systems, fountains, and baths that were carefully planned and built. Such structures required knowledge of geometry and volume in order to distribute the water evenly and keep the facilities functional. Even though no written mathematical texts from this culture have survived, the archaeological evidence speaks a clear language. Without mathematical knowledge, such a degree of organization would not have been possible. Another indication of mathematical thinking in the Indus culture are the finds of markings on shells and ivory, which are interpreted as calculation aids. Some researchers even suspect that early forms of geometry were used, for example, in the creation of blueprints or in the production of jewelry patterns. There is evidence that the Indus culture had a deep understanding of symmetry and proportion, which was evident not only in practical but also in aesthetic contexts. After the decline of the Indus culture, mathematics continued to develop in India, and here it played a prominent role in world history. Even in the early Vedic texts, which were written around 1000 BC, numbers and mathematical terms can be found. Later, in the so-called Solba Sutras, which were written between about 800 and 500 BC, it becomes clear how far geometric knowledge had progressed. These texts were mainly used to build sacrificial altars, which had to be erected according to exact proportions. The Solba Sutras contain rules for the construction of squares, rectangles, and circles. It is particularly noteworthy that they describe methods for calculating diagonals that correspond to the Pythagorean theorem. Long before the Greeks formalized this theorem, Indian scholars were already familiar with its practical application. Approximations for square roots can also be found in these texts, an indication of an astonishing mathematical maturity. But India was to make a far more significant contribution, the development of the decimal system with 0 as an independent number. This innovation, which was fully mature in the first millennium AD, revolutionized mathematics. While other cultures used cumbersome systems such as Roman numerals, the Indian place value system allowed simple calculations with large numbers. The 0 as a placeholder and number at the same time was an ingenious invention that only reached Europe through the Arabs and laid the foundation of modern mathematics there. At the same time, important mathematical traditions also developed in China. As early as the second millennium BC, there are references to arithmetic sticks that were arranged on wooden tables and enabled a flexible place value system. These rods could not only be used to perform simple calculations, but also complicated operations such as root extractions or fractions. A key work of Chinese mathematics is the 9 chapters on mathematics, Zhujiang Suanshu, which was written around 200 BC but summarized older traditions. It contains hundreds of tasks that deal with practical problems, trade, and construction. For example, there are methods for calculating areas, volumes, grain distributions, and even for solving linear systems of equations. These texts show that Chinese mathematics was a decidedly practice-oriented, but at the same time, theoretically highly developed branch. The early use of negative numbers in China is particularly noteworthy. While negative numbers were still viewed skeptically in Europe until the late Middle Ages, Chinese mathematicians used them as a matter of course, for example, to represent debt. Breaks and proportions were also part of their repertoire. Later, in the 5th century, the mathematician Zhu Changzi developed a particularly accurate approximation of pi with the value 355 by 113, which was the most accurate known for centuries. Both India and China show that mathematics did not only originate in the Middle East and on the Nile, but that different cultures developed and deepened mathematical knowledge independently of each other. Each of these traditions had its own focus. In India, the focus was on numbers, place, and symbolic notation. In China, on methods of practical calculation and algebra. Together, they decisively shaped the further history of mathematics. The early Asian contributions make it clear that mathematics has always been a universal phenomenon. It arose wherever people wanted to create structures, solve problems, and pass on knowledge. Whether in the brick measures of Harappa, the sacrificial altars of Vedic India, or the arithmetic sticks in ancient China, the same principle was evident everywhere. The human mind seeks order, patterns, and predictability. This diversity of origins would later form the basis for the exchange between cultures that made mathematics a global science. Chapter 5. Mathematics in Ancient Greece from Thales to Pythagoras. With the rise of Greek culture in the 6th century BC, a new era of mathematics began. While the early advanced civilizations of Mesopotamia, Egypt, or India had used mathematics primarily as a practical tool, a new understanding developed among the Greeks. Mathematics was regarded as an independent science, as a system of truths that not only served to solve everyday problems, but could also form the foundation of philosophy and knowledge of nature. This is where the tradition begins that we still associate with the word theory today. A key figure in this early phase was Thales of Miletus, who lived around 600 BC. He is often considered the first mathematician in Greece, and he is said to have learned the knowledge of the geometers there during a trip to Egypt. The story is famous that he determined the height of the pyramids by comparing their shadow with that of his own body, a vivid example of the application of geometric principles. Thales is also credited with the insight that a semicircle has a right angle over the diameter, an insight that he not only observed but also tried to prove. This was the beginning of the idea that mathematical statements have general validity and are not based solely on experience. Another decisive step was taken with Pythagoras of Samos, who worked in the 6th century BC. Pythagoras and his followers, the Pythagoreans, regarded mathematics not only as useful but as the basis of the world order. Their famous motto, "Everything is number," expresses this thinking. They saw the structure of harmony in the ratios of numbers, not only in geometry but also in music, where they discovered the mathematical proportions of tone intervals. The best known is the Pythagorean theorem, named after Pythagoras, which describes the relationship between the sides of a right-angled triangle. Although this knowledge was also known in Babylonia and India, the Pythagoreans elevated it to a general mathematical principle. The decisive factor was not only the knowledge of the rule, but the attempt to prove it systematically. With this, Greek mathematics took a new path. It became the science of proofs, in which it was not enough to know something, it had to be justified. However, the Pythagoreans also discovered something that shook their world: the existence of irrational numbers. When examining the diagonal of a square, they found that their relationship to the length of the side could not be represented as a fraction of two integers. This knowledge was so shocking that it was supposedly kept secret because it challenged the idea that everything is number. Here, it was shown for the first time that mathematics could not only produce answers, but also new, difficult questions. Greek mathematics was closely linked to philosophy. For thinkers like Plato, it was the epitome of clarity and truth. In his academy, which is considered one of the first universities, it is said to have written above the entrance, "No surveyor enters here." In doing so, he made it clear that no real philosophy is possible without mathematical thinking. Mathematics became the key to understanding the order of the cosmos, and geometry was considered the purest form of this science. An important aspect of Greek mathematics was the turn to the abstract. While the Egyptians and Babylonians calculated areas and volumes to measure fields or plan supplies, the Greeks developed geometry as a system of axioms and theorems. Characters were not only drawn, but thought. Triangles and circles were no longer just practical objects, but ideal shapes that existed independently of reality. This thinking laid the foundation for a mathematics that was not based on experience, but on logic. In addition to geometry, the Greeks were also concerned with arithmetic and astronomy. They developed theories of proportions, dealt with prime numbers, and began to explain the sky with mathematical models. Early on, they realized that the movements of the planets were not arbitrary, but regular. Here, too, mathematics was not just a tool, but a language with which the world could be described. Early Greek mathematics, from Thales to Pythagoras to the Sophists, was thus a radical new beginning. It elevated mathematics to a science whose goal was not only practical usefulness, but also the recognition of eternal truths. This idea shaped European intellectual history well into modern times. But as much as the Greeks concentrated on the abstract, the connection to practice remained. Whether in the construction of temples, in the planning of cities, or in astronomy, mathematical findings have always found their way into reality. The difference was that they were now on a new basis, on proofs, on logic, on the conviction that mathematics was not only useful, but true. This opened a new chapter in the history of mathematics. The counts of the Stone Age and the calculations of the advanced civilizations had become a science that claimed to have universal validity. From now on, mathematics was not only to order the world, but also to shape the foundations of philosophy and the natural sciences.
Chapter 6: Euclid and the Emergence of Geometry as a Science. With the rise of Greek mathematics in the classical period, a foundation was laid that still exists today. At the center of this development is the name Euclid, a scholar who worked in Alexandria in the 3rd century BC. His work, Elements, is considered one of the most influential books in human history. It brought order to the knowledge of its time and elevated geometry to a rigorous science, no longer based on experience but on evidence. Alexandria, the capital of Hellenistic Egypt, was a center of knowledge. After the death of Alexander the Great, his successors, the Ptolemies, founded the famous library here, which attracted scholars from all over the world. It was in this atmosphere of intellectual flowering that Euclid worked. We know little about his life. He was probably a teacher and researcher, perhaps from Athens, but certainly someone who systematized the findings of the Greeks and preserved them for future generations. The Elements consist of 13 books that cover an incredible range of mathematical topics, from plane geometry to number theory and spatial geometry. But it was not only the content that was decisive, but the method. Euclid began with axioms, i.e., basic assumptions that were so self-evident that they needed no further justification. From these axioms, he derived sentences, step by step, each building on the previous ones. In doing so, he created a system based on clear logic. A well-known example is the definition of the point. A point is that which has no parts. This is how geometry begins in the Elements. From here, Euclid develops lines, surfaces, and solids. Every sentence is proven, not just asserted. This creates a chain of knowledge that rests on solid foundations.
This approach became a model for all mathematics and still shapes it today. The Euclidean proofs for the Pythagorean theorem, for the infinity of prime numbers, or for the properties of circles and triangles are famous. Particularly impressive is the proof that there are an infinite number of prime numbers. Euclid argues by assuming that there are only finitely many, and then shows that their product plus 1 results in a new number that is not divisible by the known prime numbers. With this simple but ingenious idea, he laid the foundation for number theory. The effect of the elements was immense. For 2 millennia, this work was considered the standard textbook of mathematics. It was copied in countless manuscripts, translated into many languages, and served as the basis of mathematical teaching until the 19th century. Newton and Gauss still learned with Euclid, and even today his method is a model for logical thinking. But the importance of Euclid lies not only in the content, but also in the philosophy he conveyed. For him, mathematics was no longer just a collection of rules or procedures, but a self-contained system of truths. This idea became the guiding principle of Western science, the pursuit of evidence, of logical consistency, of a building of knowledge that stands on secure foundations. Euclidean geometry also shaped the image of the world. For centuries, it was considered the only possible description of space. Lines, dots, and planes seemed to determine the structure of the universe. It was not until the 19th century that mathematicians such as Lobachevsky or Riemann dared to question this order and develop non-Euclidean geometries. But even these revolutions would not have been conceivable without Euclid, because they started with the foundations he had formulated. It is interesting that the elements also have an aesthetic dimension. Many scholars saw in the clarity of Euclidean evidence a beauty that went beyond mere utility. Mathematics was understood as the art of the mind, as an expression of pure reason. This attitude influenced philosophers such as Aristotle, who considered mathematics as an example of certain knowledge, and centuries later, Kant, who saw Euclidean geometry as a model of a priori knowledge. In addition to geometry, Euclid also dealt with arithmetic and proportions. He systematized the knowledge of prime numbers, divisibility, and greatest common factors. His methods, such as the so-called Euclidean algorithm for calculating the greatest common factor, are still in use today. In doing so, he connected the world of numbers with that of forms, and showed that mathematics forms a unity. Euclid was not the only important mathematician of his time, but his work bundled the traditions and made them permanently accessible. Contemporaries such as Archimedes continued to develop mathematics, but without the basis of the elements, much would have been lost. When we speak of Euclid today, we are not only thinking of a scholar, but of the beginning of a new epoch. With him, mathematics finally became a science based on proofs and logical structure. His ideas not only survived for centuries, but also shaped thinking about truth, knowledge, and science in general. The elements are a symbol that mathematics is more than arithmetic or counting. It is a system that reflects the order of the world. From ancient geometers to medieval scholars to modern mathematicians and philosophers, Euclid remained the benchmark. Even in school, when children today learn geometric proofs, they still follow the spirit that he founded in Alexandria over 2,000 years ago.
Chapter 7. Archimedes and the connection between theory and practice. If there is one name that stands for the genius of ancient mathematics like no other, it is Archimedes of Syracuse. Born around 287 BC in the Greek colony of Syracuse in Sicily, he combined profound theoretical insights with astounding practical inventions like hardly anyone before. His person shows that mathematics can not only be an abstract science, but also a source of technical innovation and practical applications. Archimedes is considered one of the greatest mathematicians of all time. His writings, of which only a part have survived, show an astonishing variety. He dealt with geometry, number theory, mechanics, hydrostatics, and even with precursors of integral calculus. His thinking was imbued with an extraordinary ability to present abstract problems and exact proofs, and at the same time to find solutions that could be used immediately in practice. One of his best-known achievements was the development of lever laws. Archimedes realized that with a lever long enough and a fixed point, you could move almost any weight. Give me a fixed point and I will turn the world upside down. This sentence attributed to him expresses the fascination that emanated from his discovery. Here, he combined mathematical principles with physical reality and created the foundations for mechanics, which were further developed thousands of years later in modern physics. No less famous is his work on hydrostatics. Archimedes realized that when a body is immersed in a liquid, it experiences buoyancy equal to the weight of the displaced liquid. This insight, known as Archimedes' principle, still forms the basis for shipbuilding today. Legend has it that he made this discovery in the bathtub and shouted naked through the streets, "Eureka! I found it!" Even if this anecdote is probably more of a literary embellishment, it shows how much his discoveries were connected with vivid observations of everyday life. However, Archimedes was not only a naturalist, but also a master of pure mathematics. He worked intensively on the geometry of surfaces and bodies. His calculation of the ratio between sphere and cylinder is particularly famous. The volume of a sphere is 2/3 of the volume of a cylinder circumscribing it. Archimedes was so proud of this discovery that he wished to depict this relationship on his grave. This work shows his ability to penetrate complex geometric problems through logical proofs, an anticipation of methods that would lead to integral calculus centuries later. The determination of circular areas and the approximation of the number pi can also be traced back to Archimedes. He calculated the area of the circle by narrowing it between polygons that were inscribed and rescribed. By successively doubling the number of vertices, he was able to narrow pi down to values between 3.1408 and 3.1429, an astonishing accuracy for antiquity. This method shows not only its sophistication, but also its proximity to later methods of analysis. Archimedes also dealt with infinite series and sums. In his work, The Sand Calculator, he developed a number system to express unimaginably large numbers, such as the number of grains of sand that could fill the universe. In doing so, he exceeded the limits of the number representation that was common at the time and ventured into dimensions that were only reached again centuries later by modern mathematics. No less famous is his work on hydrostatics. Archimedes realized that when a body is immersed in a liquid, it experiences buoyancy equal to the weight of the displaced liquid. This insight, known as Archimedes' principle, still forms the basis for shipbuilding today. Legend has it that he made this discovery in the bathtub and shouted naked through the streets, "Eureka! I found it!" Even if this anecdote is probably more of a literary embellishment, it shows how much his discoveries were connected with vivid observations of everyday life. However, Archimedes was not only a naturalist, but also a master of pure mathematics. He worked intensively on the geometry of surfaces and bodies. His calculation of the ratio between sphere and cylinder is particularly famous. The volume of a sphere is 2/3 of the volume of a cylinder circumscribing it. Archimedes was so proud of this discovery that he wished to depict this relationship on his grave. This work shows his ability to penetrate complex geometric problems through logical proofs, an anticipation of methods that would lead to integral calculus centuries later. The determination of circular areas and the approximation of the number pi can also be traced back to Archimedes. He calculated the area of the circle by narrowing it between polygons that were inscribed and rewritten. By successively doubling the number of vertices, he was able to narrow pi down to values between 3.1408 and 3.1429, an astonishing accuracy for antiquity. This method shows not only its sophistication, but also its proximity to later methods of analysis. Archimedes also dealt with infinite series and sums. In his work, The Sand Calculator, he developed a number system to express unimaginably large numbers, such as the number of grains of sand that could fill the universe. In doing so, he exceeded the limits of the number representation that was common at the time and ventured into dimensions that were only reached again centuries later by modern mathematics. In addition to his theoretical work, Archimedes was also a genius engineer. He constructed war machines to defend his hometown of Syracuse against Roman attacks. Contemporaries report huge catapults, mirrors that focused the sun's rays to ignite enemy ships, and huge cranes that lifted ships out of the water. Whether all these stories are historically true is disputed, but they show the reputation that Archimedes already enjoyed during his lifetime. One of his most important practical inventions was the Archimedean screw, a device that allowed water to be transported upwards through a spiral device. It was used to irrigate fields and is still used in a similar form today. Here it becomes clear how closely mathematics, technology, and everyday life can be connected. Archimedes' life ended tragically in 212 BC when Syracuse was conquered by the Romans after a long siege. Although the Roman general Marcellus had ordered Archimedes to be spared, he was killed by a soldier. With this, the ancient world lost one of its greatest scholars, but his legacy continued to have an effect. Archimedes embodies the unity of theory and practice like no other. His work shows that mathematics is not only abstract thinking, but also a tool to shape the world. He laid the foundations for mechanics, hydrostatics, geometry, and number theory, and showed that the same principles that explain the sky can also be useful in everyday life. His influence reached far beyond antiquity. In the Middle Ages, Arab scholars studied his writings and carried them to Europe. In the Renaissance, his works inspired engineers and scientists. Newton, Galileo, and other great scholars saw in Archimedes a forerunner of their own work. Even today, he is considered the epitome of mathematical genius, whose thinking combined theory and practice in a unique way.
Chapter 8. Mathematics in China. Math sticks, calendars, and the 9 chapters work. While in the Greek world, mathematics increasingly became a theoretical science, in China, it developed in a different but equally impressive way. Here, mathematics was deeply linked to the practical needs of administration, agriculture, and astronomy from the very beginning. The Chinese tradition is characterized by a remarkable balance between practice and abstraction, between arithmetic and theoretical understanding. Very early on, the Chinese used arithmetic sticks, which were made of wood or bamboo and arranged on a board or table. These rods allowed for a flexible place value system that could even represent negative numbers. With different positions and arrangements, not only simple additions and subtractions could be performed, but also multiplications, divisions, and root extractions. This system was not only elegant, but also far superior to Roman numerals, which made calculations more difficult in Europe centuries later. A central work of Chinese mathematics is the 9 chapters on mathematics, Jiuzhang Suanshu, which was compiled around 200 BC but probably contains older traditions. This work is not a theoretical treatise, but a textbook full of problems and solutions, intended for practical use. It contains over 200 problems from everyday life, administration, and technology. Topics include the distribution of grain, the calculation of fields, the determination of building volumes, the solution of systems of equations, and the application of proportions. An example from the 9 chapters describes the division of workers into a project, or the distribution of supplies, tasks that were of enormous importance to a large empire. Mathematics was directly used for administration. It was a tool for using resources efficiently and creating order in the empire. At the same time, however, processes were developed that went far beyond the practical. For example, the 9 chapters contain methods that we now understand as early forms of linear algebra. Systems of equations were manipulated with matrices long before the term was introduced in Europe. It is particularly noteworthy that the Chinese accepted negative figures early on. While skepticism about negative numbers prevailed in Europe until the 17th century, they were a natural part of computing practice in China. Using red and black sticks, they marked positive and negative values and used them to solve complex tasks.
This openness to new mathematical concepts shows the pragmatic attitude of Chinese mathematics. Everything that was useful was adopted and further developed. Mathematics also played a central role in astronomy. The Chinese developed precise calendars that were necessary to organize agricultural cycles and establish religious festivals. As early as the 4th century BC, a lunisolar calendar was used that combined solar and lunar cycles. To describe the movements of the sun, moon, and planets, Chinese astronomers used mathematical models. These observations were not only of practical importance, but were also considered the basis for the legitimation of rule, because the emperor had to rule in accordance with the mandate of heaven. Chinese mathematics was also characterized by a special strength in geometry, even if, unlike in Greece, it relied less on proofs than on methods. There are tasks on areas and volumes, on determining circular areas, or on calculating body sizes. Early on, approximations for pi were found that were surprisingly precise. In particular, the mathematician Zhu Chengji, 429 to 500 AD, achieved a value with the fraction 355 over 113 that remained the most accurate approximation known for centuries. In addition to the 9 chapters, other important works were created, which are often referred to as classical mathematics texts. These writings have been commented and expanded over centuries. They show that mathematics had a continuous tradition in China which was closely linked to the training of civil servants. Anyone who wanted to enter the civil service not only had to master literature and philosophy, but also prove mathematical knowledge. Another highlight was the work of the mathematician Liu Hui in the 3rd century AD. He commented on the 9 chapters, introducing more precise methods for calculating area and volume. Particularly well known is his method of approximating the number pi by inscribing polygons with more and more sides in a circle. In doing so, he approached the same principle that Archimedes followed, an indication that great mathematical ideas often arise independently of each other in different cultures. The calculation with polynomials and approaches to combinatorics were also widespread in China early on. The so-called Chinese remainder theorem, a method for solving certain number systems, dates back to the 3rd century AD and is still used in number theory today. Chinese mathematicians also dealt with problems that we would now call combinatorial, such as the arrangement of numbers or figures in certain patterns. Chinese mathematics as a whole shows that it was both practically oriented and theoretically highly developed. She combined the needs of a large administration with a curiosity to explore mathematical structures. She was open to new ideas, whether it was dealing with negative numbers or working with large numbers and precise approximations. While Europe was still strongly influenced by the Greek tradition in antiquity and the Middle Ages, China developed an independent mathematical path that remained of great importance until modern times. Many of their discoveries, such as calculating with place value systems, accepting negative numbers, or solving complex systems of equations, later influenced the mathematics of other cultures. Chapter 9. India as the Cradle of Zero and the Decimal System. If one had to name a single milestone that revolutionized the history of mathematics, it would undoubtedly be the introduction of the zero and the decimal system. Both developed in India and irrevocably changed the world. Without these inventions, modern mathematics, science, and technology would be hard to imagine. The Indian tradition was not only innovative, but also characterized by a special ability for abstraction and symbolic representation that went far beyond practical applications. Even in the early Vedic texts, which were written from about 1000 BC onwards, there are references to mathematical knowledge. Particularly important are the so-called Sulba Sutras, which dealt with the construction of sacrificial altars. These altars had to be constructed according to exact proportions, and the texts contain rules that correspond to the Pythagorean theorem. Approximations for square roots are also included, proof that Indian scholars had a deep understanding of geometry and arithmetic early on. But the real revolution began several centuries later, when Indian mathematicians developed a place value system based on base 10. Unlike the Romans with their complicated number symbols or the Babylonians with their base 60, the Indians used simple digits from 1 to 9, supplemented by a sign for nothing, the 0. Initially, the 0 served as a placeholder to distinguish between 10, 100, or 1000. But soon it was understood as a separate number that could be counted on. This innovation was groundbreaking. For the first time, it was possible to display large numbers with few symbols and perform complex calculations easily. Multiplication, division, and exponentiation became much more efficient as a result. The Indian numeral system was so superior that it was later adopted by Arab scholars and brought to Europe. Today, we know it as the Arabic numerals, although they are actually of Indian origin. However, Indian mathematics was not limited to the introduction of 0. Scholars such as Aryabhata, 476 to 550 AD, developed comprehensive mathematical works that dealt with algebra, trigonometry, and astronomy. Aryabhata described methods for calculating squares and cubes, gave approximations for pi, and introduced trigonometric functions, which he referred to as sine and cosine. These functions would later play a central role in astronomy and physics. Another important mathematician was Brahmagupta, 598 to 66 AD. In his work Brahmasputa Siddhanta, he laid down rules for dealing with the 0 and negative numbers. He explained that a number minus itself is 0, that 0 multiplied by any number is 0, and that a number divided by 0 is indeterminate. Even if modern mathematics differentiates the latter even more precisely, this shows how far ahead of its time Brahmagupta's thinking was. Brahmagupta also worked on Diophantian equations, i.e., equations with integer solutions. He developed methods to find solutions to quadratic equations, thus laying the foundation for number theory. His works were later translated into Arabic and had a significant influence on Islamic mathematics. In the 12th century, Bhaskara II, 1114 to 1185. In his work Lilavati, he dealt with a variety of mathematical problems in poetic form, often in the form of riddles and stories. This work was not only a textbook, but also a literary work of art that made mathematics accessible and vivid for students. Bhaskara dealt with algebra, analysis, and astronomy, and even recognized the first approaches to calculus, which was systematized centuries later in Europe by Newton and Leibniz. Indian mathematics was characterized by its close connection to astronomy. Many mathematical innovations arose from the need to calculate celestial movements and create calendars. The observation of solar and lunar eclipses, the determination of planetary orbits, and the prediction of seasons required exact mathematical methods. Trigonometry and algebra therefore developed in close exchange with astronomy. The teaching of mathematical knowledge was also particularly diverse in India. Mathematics was not only practiced as a sober science, but was often passed on in the form of poems and songs. This made memorization easier and made complicated rules memorable. The combination of mathematics and language shows the cultural peculiarity of India, where knowledge has always had an aesthetic dimension. The importance of Indian mathematics for world history can hardly be overestimated. Without the 0 and the decimal system, modern science would be inconceivable. Whether in algebra, astronomy, or analysis, the Indian foundation can be felt everywhere. The adoption of these ideas by Arab scholars and their spread to Europe fundamentally changed mathematics and created the basis for the scientific revolution of modern times. This made India the real cradle of modern mathematics. The ability to symbolize nothingness and to reckon with it was not only a technical achievement, but also a philosophical step. It showed that abstraction has a power that can break the boundaries of the imaginable. The void became a number, and from this number grew a new world of possibilities.
Chapter 10: Arabic Islamic Mathematics, Algebra, Astronomy, and the Heritage of Antiquity. With the rise of the Islamic world in the 8th and 9th centuries, a new heyday of mathematics began. While in Europe the knowledge of antiquity had largely been forgotten, scholars in Baghdad, Damascus, Cairo, and Cordoba created an intellectual network that combined ancient, Indian, and their own knowledge. They translated Greek and Indian works into Arabic, developed new methods, and thus laid the foundation for many achievements that later reached Europe and fueled the Renaissance there. At the center of this movement was the House of Wisdom in Baghdad, founded in the 9th century under Caliph al-Ma'mun. Translators, mathematicians, astronomers, and philosophers worked together here. Greek texts by Euclid, Archimedes, and Ptolemy were translated into Arabic, as were Indian works such as the treatises of Aryabhata and Brahmagupta. This cultural exchange created a unique foundation of knowledge on which Islamic scholars developed their own innovations. One of the most famous among them was al-Khwarizmi, k. 780 to 850. His name lives on to this day in terms such as algorithm and algebra. In his work Al-Kitab al-Mukhtasar fi Hasab al-Jabr wal-Muqabala, he presented methods for solving quadratic equations and thus established algebra as an independent discipline. The term al-Jabr that enters the title means restoration or complement and became algebra in Europe. Al-Khwarizmi systematized procedures that arose from practical needs, such as inheritance divisions, trade transactions, or land surveys, and combined them into a general theory. Equally important was its role in the spread of the Indian numeral system. In his writings, he explained the handling of the digits from 1 to 9 as well as the 0. Through his works, the Indian numerals reached the West, where they became known as Arabic numerals. Without this mediation, European mathematics would probably have remained stuck in the complicated Roman numerals for a long time to come. In addition to al-Khwarizmi, numerous other scholars shaped Islamic mathematics. Al-Kendi studied number theory and cryptography. Thabit ibn Qurra translated Greek classics and developed theories about number sets. And al-Karaji continued algebra by systematically treating powers and polynomial operations. Later, in the 11th century, Omar Khayyam, who also became famous as a poet, brought significant progress in solving cubic equations. He realized that these could not always be solved by pure algebra and applied geometric methods, an indication of the close connection between algebra and geometry. Islamic mathematics also excelled in astronomy. Calendar reforms, the determination of prayer times, and the orientation of mosques towards Mecca required precise calculations. Astronomers such as al-Battani determined the length of the solar year more accurately than Ptolemy, and al-Tusi developed trigonometric models that later influenced Copernicus. Trigonometry in particular took on a systematic form during this time. While the Greeks mainly worked with tendons, Islamic mathematicians introduced functions such as sine, cosine, and tangent, which still form the basis of trigonometry today. The optics and geometry also experienced progress. Ibn al-Haytham al-Hazan, who worked in the 10th and 11th centuries, is considered the founder of modern optics. His experiments with light and mirrors showed the importance of mathematical models for the natural sciences. In geometry, the Euclidean legacy was carried on, but also critically questioned. Discussions about the axiom of parallels, which remained an unsolved problem in Euclid's Elements, already pointed to the later developments of non-Euclidean geometry. Another important field was arithmetic. Islamic scholars developed methods for calculating large numbers, worked with fractions, and introduced new calculation techniques. These skills were indispensable, especially in trade and administration. Mathematics schools existed in many cities, and works such as al-Khwarizmi's served as practical textbooks that were used far beyond the learned elite. However, Islamic mathematics was not only a science in itself, but also a medium of cultural mediation. Through Spain and Sicily, many Arabic texts reached Europe, where they were translated into Latin in the Middle Ages. Names such as al-Khwarizmi or al-Battani became algorism and albategnius in the Western world. In this way, the knowledge of the Islamic world flowed directly into the European tradition and formed the basis for the Renaissance there. The importance of this epoch lies not only in its innovations, but also in its role as a bridge. Without the translations and commentaries of Arab scholars, many works of Greek antiquity would have been lost. At the same time, they expanded knowledge of Indian and own contributions. Algebra, trigonometry, number theory, all of these were not only preserved during this time, but decisively advanced. Arabic Islamic mathematics shows how strongly science thrives on cultural exchange. It was not an isolated phenomenon, but the result of a meeting of traditions brought together in the House of Wisdom. Here, the practical need of administration and religion was combined with a philosophical urge for knowledge, and from this connection arose a mathematics that lasted for centuries and shaped the world.
Chapter 11. Medieval Europe: Translations, Monasteries, and Scholasticism. While mathematics flourished in the Islamic world and in India, Europe experienced a phase after the collapse of the Western Roman Empire, which is often referred to as Dark Centuries. The knowledge of antiquity was not completely lost, but it was preserved in fragments, mostly in monasteries where monks copied writings. At that time, mathematics was closely linked to church education and served mainly practical purposes, such as calculating the calendar or the liturgy. The basis of medieval education was formed by the so-called 7 liberal arts, which were divided into trivium, grammar, rhetoric, dialectics, and quadrivium, arithmetic, geometry, music, and astronomy. Within the quadrivium, mathematics occupied a firm place, but it was more philosophical than practical. Numbers were considered an expression of divine order, and the preoccupation with them often had a symbolic meaning. Thus, the number 3 was seen as the Trinity, in the number 7, perfection, in the number 12, the divine order. Practical mathematics nevertheless played a role. Monasteries had to manage their lands, calculate supplies, and carry out construction projects. In the construction of large cathedrals in the High Middle Ages, knowledge of geometry was used, even if it was often more manual than theoretical. The Gothic style, with its precise proportions, arches, and vaults, would not have been possible without mathematical knowledge. A decisive turning point came from the 12th century onwards, when Europe gained access to the treasures of the Arab Islamic world via Spain and Sicily. In cities such as Toledo, schools of translation sprang up, in which scholars translated Arabic texts into Latin. Thus, the works of Al-Khwarizmi, Al-Battani, and others came to Europe, as did the Greek classics, which had been preserved through Arab mediation. With these translations, not only Euclid and Archimedes returned, but also the Indo-Arabic numeral system. In particular, the introduction of the 0 and the Arabic numerals represented a huge advance over the Roman numerals. The Italian merchant Leonardo of Pisa, better known as Fibonacci, played a key role here. In his work Liber Abaci of 1202, he introduced the new number system and used practical examples to show how superior it was. His famous Fibonacci sequence, which emerged from a problem with rabbit reproduction, also made him famous. Scholasticism, which shaped the universities in the High Middle Ages, combined theology and philosophy with mathematical thinking. Numbers were not only understood as tools, but as the key to creation. Scholars such as Thomas Aquinas saw mathematics as proof of the divine order of the world. At the same time, universities such as Paris, Bologna, or Oxford began to teach mathematics as part of the curriculum, as a result of which the knowledge spread systematically. Astronomy was also closely linked to mathematics. The calculation of the church calendar, especially the date of Easter, required complicated calculation methods. The preoccupation with the sky led to the resurrection of ancient models, but also to the development of new panels and instruments. In particular, the astrolabe, a device for determining star positions, became an important tool for astronomers and sailors.
In the late Middle Ages, the importance of mathematics grew due to the emergence of trade and the money economy. Merchants needed knowledge of arithmetic, bookkeeping, and exchange rates. Trading cities such as Florence, Venice, and Lubeck became centers of practical mathematics. Schools for arithmetic masters were created in which young people learned methods for everyday life. Here, mathematics began to step out of pure scholasticism and to orient itself more strongly towards the needs of society. Despite these advances, medieval mathematics remained restrained compared to the advanced civilizations in India, China, or the Islamic world. It was characterized less by innovation than by preservation and transmission. But it was precisely this role that was decisive. Through translations, monasteries, and universities, Europe gained access to a treasure that would later form the basis for the Renaissance and the scientific revolution. Medieval mathematics shows that knowledge does not always grow linearly. Sometimes it is preserved, sometimes rediscovered, sometimes expanded only in small steps. Without the patient work of the monks who copied writings, without the translators of Toledo who translated Arabic texts into Latin, and without the arithmetic masters who spread the Indian numeral system, the great boom of the modern era would not have been possible.
Chapter 12. The Renaissance, Rediscovery, and New Impulses. With the beginning of the Renaissance in the 14th and 15th centuries, Europe experienced an intellectual renewal that also affected mathematics. While the Middle Ages mainly preserved the ancient writings, people now began to study them anew, critically question them, and develop them further. The rediscovery of man as the measure of all things, the flourishing of art, architecture, and the natural sciences, and the expansion of trade led to mathematics taking on a completely new meaning. It became the tool of a world that was changing rapidly. A key factor was humanism, which propagated a return to the sources of antiquity. Scholars scoured monasteries for ancient manuscripts, translated Greek texts from the original, and recirculated works such as Euclid's Elements or Archimedes' writings. But this time, they were not only admired, but also used as a basis for new developments. Mathematics became the core of a new scientific culture in which observation, experimentation, and computation came together. The art of perspective, which was developed in 15th century painting, played a decisive role. Artists such as Brunelleschi and Alberti realized that space could be represented mathematically. With the help of vanishing points and geometric constructions, it was possible to realistically bring depth and spatiality to the canvas. Mathematics thus became a bridge between art and science, an expression of the Renaissance idea that everything was connected. Architecture also benefited from mathematical thinking. Buildings such as the dome of Brunelleschi's Florentine Cathedral or the churches of Palladio testify to an understanding of proportion, statics, and geometry that went far beyond the purely handcrafted. The beauty of these buildings lay not least in the mathematical harmonies they embodied. At the same time, astronomy experienced an upheaval. Nicholas Copernicus published his work De Revolutionibus Orbium Celestium in 1543, in which he placed the sun at the center of the worldview. This heliocentric model was only possible through elaborate mathematical calculations. Copernicus resorted to trigonometry, as developed by Arab and Indian scholars, and linked it to the Euclidean legacy. This marked the beginning of a scientific revolution that would have been inconceivable without mathematics. Great progress was also made in the field of arithmetic. The Indo-Arabic numeral system, which had slowly gained a foothold in the Middle Ages, now finally prevailed. Merchants, banks, and trading companies used it to make bookkeeping and interest calculations more efficient. In Italy, the so-called arithmetic schools were established, in which young people learned the new methods. Works such as the Treviso Arithmetics book of 1478 or the writings of Luca Pacioli, the father of accounting, systematically disseminated knowledge.
Pacioli, a contemporary of Leonardo da Vinci, wrote the Summa de Arithmetica Geometria Proportionia et Proportionalita, 1494, which is considered a comprehensive textbook of mathematics at the time. It covered arithmetic, algebra, geometry, and practical applications such as accounting. His presentation of double-entry bookkeeping, which is still the basis of modern accounting today, became particularly well known. The Renaissance also advanced algebra. In Italy, mathematicians such as Scipione del Ferro, Niccolò Tartaglia, and Girolamo Cardano developed methods for solving cubic and biquadratic equations. Cardano published the work Ars Magna in 1545, in which he systematically presented these solutions. This marked the beginning of a new phase in which algebra rose from a practical tool to a theoretical discipline. Another milestone was the emergence of modern symbolism. While antiquity and the Middle Ages often used long sentences to describe mathematical operations, Renaissance mathematicians introduced signs for plus, minus, and equality. This symbolization made mathematics more precise and easier to handle. Prose written out became concise formulas that made complex relationships quickly comprehensible. The invention of the printing press intensified this change. Mathematics could now be disseminated in large numbers, no longer just as a handwritten manuscript for a small elite. Textbooks, blackboards, and tables found their way into universities, schools, and trading houses. This increased the reach of mathematics enormously, and it became part of a broad education. The connection between mathematics and technology also intensified. The construction of cannons, the calculation of trajectories, and the development of new navigation instruments required exact calculation methods. The voyages of discovery of the Portuguese and Spaniards would hardly have been possible without mathematical knowledge of navigation, especially trigonometry and astronomy. The Renaissance was therefore a time in which mathematics received new impulses from all sides, from the rediscovery of antiquity, from the demands of art and architecture, from the needs of trade and technology, and from scientific curiosity. It was no longer just one discipline among many, but became the heart of a new worldview. When you look at this epoch, it becomes clear how much mathematics can be a bridge between the past and the future. It preserved the knowledge of the Greeks, integrated the contributions of the Arabs and Indians, and laid the foundations on which the great discoveries of modern times, from Kepler to Galileo to Newton, could be built. The Renaissance was thus not only a rebirth of art, but also a rebirth of mathematics.
Chapter 13. La Berta di moderna algebra e numeri teoria. After the rebirth of science in the Renaissance, mathematics entered a new phase in the 16th and 17th centuries. It became increasingly abstract, systematic, and universal. Algebra, in particular, developed from a tool for solving concrete problems to a general theory that focused on symbols and structures. At the same time, number theory emerged as an independent field of research that not only pursued practical purposes, but also explored the inner laws of numbers themselves. Italian mathematicians had already laid the foundations in the late Middle Ages. Scipione del Ferro found a method for solving cubic equations, but he kept it secret. His pupil Antonio Fior tried to use this knowledge, but it was Niccolò Tartaglia who discovered the process in the 16th century, which he initially only partially revealed. Finally, in 1545, Girolamo Cardano published in his Ars Magna a systematic presentation of the solutions for cubic and biquadratic equations. This work is considered the birth of modern algebra. The Ars Magna was more than a collection of computational methods. She introduced new symbolic notations and showed that algebraic problems could be studied independently of practical applications. With the solution of the cubic equation, mathematics began to detach itself from concrete numbers and to bring the abstract to the fore. Another key event was the introduction of new counting ranges.
In the solution of certain equations, negative and even imaginary numbers appeared. While negative figures were still viewed with skepticism, the roots of negative figures initially caused great astonishment. They were called wrong or impossible numbers, but gradually they were accepted as useful tools. The expansion of the concept of numbers was a decisive step towards modern mathematics. In the 17th century, significant innovations were added. François Viet is considered the founder of symbolic algebra. He systematically introduced letters for known and unknown quantities and formulated equations in general form. Thus, algebra finally became a language that could express abstract structures. Viet understood algebra not only as an art of arithmetic, but as a universal instrument that made relationships visible and revealed regularities. At the same time, number theory emerged as an independent field. The Greeks had already dealt with prime numbers, but it was not until modern times that systematic research began. Pierre de Fermat made numerous conjectures, including his famous last theorem, which was not proven until the 20th century. Fermat investigated properties of prime numbers, divisibility and congruencies, thus laying the foundation for a discipline that still plays a central role today, not only theoretically but also practically, for example in modern cryptography. Marin Mersenne, a contemporary of Fermat, also dealt with special numbers, which later became known as Mersenne prime numbers. These numbers of the form 2 to the p-1, where p is a prime number, fascinated mathematicians for centuries and are still the subject of current research today. The search for large Mersenne prime numbers has even found its way into modern computer projects. The development of algebra also led to the emergence of new structures. In the 17th century, mathematicians began to systematically study higher-order equations. Although it soon became clear that there could be no general solution formula for equations of the fifth degree, a result that was not definitively proven until the 19th century by Abel and Galois, the search for such solutions continued to drive the development of algebra. A milestone in the dissemination of algebraic knowledge was the work of René Descartes. In his Discours de la méthode of 1637, he published La Geometria, in which he combined algebra and geometry. With the introduction of the coordinate system, geometric figures could be described by equations. This analytic geometry opened up a completely new view in which algebra became the tool of geometry and vice versa. The birth of modern algebra was closely linked to the new symbolic language. Signs of equality, powers, roots, and operations made the presentation shorter, more precise, and more general. This made mathematics not only more efficient, but also more universally understandable. It was transformed into a language of science that could be applied regardless of culture or region. Overall, this epoch was characterized by a double process, abstraction and expansion. Abstraction meant that mathematicians no longer only solved concrete problems, but investigated general structures. Expansion meant that the concept of numbers was constantly expanded, from natural numbers to negative numbers to fractions to irrational and imaginary numbers. Each of these extensions initially met with resistance, but eventually prevailed because it made mathematical thinking richer and more powerful. Number theory and modern algebra, which were born during this period, are still cornerstones of mathematics today. They shape not only pure research, but also applications in technology and computer science. The fact that it is possible to calculate secure data transmissions or complex physical models is ultimately due to the epoch in which mathematicians began to understand numbers and symbols as independent objects of a universal science.
Chapter 14. The Development of Analysis. Newton, Leibniz, and the Infinite Small. The 17th century was not only the time of great discoveries in astronomy and physics, but also the epoch in which mathematics experienced one of its most important revolutions, the emergence of analysis.
It made it possible to capture movement, growth, change, and the infinite in a precise mathematical language. Two names are at the center of it: Isaac Newton and Gottfried Wilhelm Leibniz. Both developed the foundation of differential and integral calculus almost simultaneously, but independently of each other. The way there was marked by a lot of preparatory work. Archimedes had already calculated areas under curves using methods of exhaustion, and in India and the Islamic world, there were methods for summing infinite series. In Renaissance Europe, mathematicians such as Cavalieri dealt with the method of the indivisible, a precursor of integral calculus, and Fermat developed approaches for determining tangents and extrema. All these ideas eventually led to the great synthesis of Newton and Leibniz. Isaac Newton, 1643 to 1727, developed his form of analysis as part of his physical research. In order to understand the motion of the planets, the laws of falling, and the dynamics, he needed a new mathematics. In his Principia Mathematica of 1687, he formulated the laws of mechanics and gravitation using methods that we now call differential and integral calculus. For Newton, analysis was a tool to put the laws of nature into mathematical form. Gottfried Wilhelm Leibniz, 1646 to 1716, on the other hand, came from philosophy and logic. He developed his own form of analysis independently of Newton, but almost simultaneously. In 1684, he published the first treatise on differential calculus. Leibniz introduced an elegant symbolism that has prevailed to this day: the d for differentials, the integral sign for integrals. While Newton understood analysis more geometrically and physically, Leibniz created a symbolic language that made abstract calculations possible. The double discovery led to a bitter priority dispute that divided the scientific world. English mathematicians sided with Newton, while continental Europe preferred Leibniz. This conflict led to English mathematics being sidelined for a century, as it adhered to Newton's geometric notation, while Leibniz's symbolism allowed for rapid development on the continent. The analysis dealt with two fundamental problems: the determination of tangents and the calculation of areas. Tangent determination was about calculating the slope of a curve at a point, the central topic of differential calculus. The area calculation was about the sum of an infinite number of small stripes under a curve, the task of integral calculus. Newton and Leibniz recognized that both problems are related. Differentiation and integration are inverse processes, as it was later formulated in the fundamental theorem of analysis. The introduction of the infinite played a decisive role in this. In analysis, infinitely small quantities, the differentials, and an infinite number of summands were used. These concepts were philosophically controversial, but they proved to be incredibly fruitful. It was not until the 19th century that the strict definition of the limit value succeeded in giving analysis a firm foundation. Nevertheless, the intuition of Newton and Leibniz was so powerful that their methods were immediately applicable and revolutionized science. Analysis was quickly used in many areas. In physics, it was indispensable for mechanics, astronomy, and optics. In astronomy, it allowed exact orbital calculations of planets and comets. In terms of technology, it facilitated the construction of machines and bridges. It became a universal tool that was used wherever change, movement, or growth was involved. The endless rows also came to the fore. Leibniz investigated the sum of the reciprocal values of the square numbers and formulated the series 1 minus 1/3 plus 1/5 minus 1/7 plus ... which is used to calculate pi. Newton developed methods to represent functions by infinite series, a precursor of the later Taylor and Power series. This made it possible to approximate and calculate complicated functions that were previously inaccessible. The philosophical dimension of analysis was also significant. For Leibniz, it was an expression of his conviction that the world was ordered in a divine harmony that could be expressed in clear symbols. For Newton, it was proof that nature could be grasped in mathematical laws. In both cases, mathematics became a language that explained the universe more precisely and comprehensively than ever before. Newton and Leibniz marked the beginning of an era in which mathematics was inextricably linked to the natural sciences. Analysis became the foundation of modern physics and technology, and it has remained so to this day. Whether in the calculation of trajectories, in the modeling of populations, or in the differential equation which describes the behavior of electrical circuits, the idea of the infinitely small and the infinitely many lives on everywhere. The development of analysis shows how much mathematics is based on the ability to go beyond the immediate horizon of experience. It makes the invisible visible, infinite processes, infinitely small quantities, the continuum of movement. It is an example of how abstraction and intuition can work together to grasp reality in a new depth.
Chapter 15. Mathematics of the Enlightenment. Euler, D'Alembert, and Lagrange. The 18th century was marked by the Age of Enlightenment, in which reason, science, and progress became central leitmotifs. During this time, mathematics also experienced a tremendous expansion. The foundations laid by Newton and Leibniz in the 17th century were now systematized, expanded, and applied to a variety of new problems. Names such as Leonhard Euler, Jean-Laurent D'Alembert, and Joseph-Louis Lagrange are at the heart of this era. They made analysis a powerful tool, further developed mechanics, and shaped almost all areas of mathematics. Leonhard Euler, 1707 to 1783, a Swiss mathematician, is considered one of the most prolific scholars in history. With over 800 published papers, he shaped almost every field of mathematics. He systematized analysis, introduced new terms and notations, and made them accessible to generations of scholars. Many symbols that we use today as a matter of course, such as E for Euler's number, I for the imaginary unit, f of x for functions, or pi for circle number, can be traced back to Euler. His clarity and didactic talent made mathematics a language that could be understood universally. Euler worked on infinite series, differential equations, function theory, and number theory. He proved the famous theorem that the sum of the reciprocals of the squares gives pi squared over 6, a result known as the Basel problem. He also investigated the distribution of prime numbers, thus laying the foundations for modern number theory. In geometry, he developed Euler's famous polyhedron formula V minus E plus F equals 2, which is still one of the basic laws of topology today. In addition to his theoretical work, Euler was also a man of practice. He worked for the academies in St. Petersburg and Berlin and dealt with navigation, ballistics, music theory, and engineering. His ability to apply abstract mathematics to concrete problems made him a key figure in the Enlightenment, in which mathematics was considered the engine of progress. Another important mathematician of this period was Jean-Laurent D'Alembert, 1717 to 1783. He is not only known as the co-author of the famous Encyclopedia, but also as the founder of important methods in analysis and mechanics. D'Alembert formulated the differential equation of wave motion, which was named after him, and laid the foundations for mathematical physics. In particular, his principle of virtual work became a cornerstone of mechanics, which is still used in engineering today. D'Alembert was also a sharp critic of unclear terms in analysis. He demanded a stricter justification of the infinitely small quantities introduced by Newton and Leibniz. In doing so, he prepared the ground for the later work of Cauchy and Weierstrass, which gave analysis a rigorous foundation in the 19th century. Joseph-Louis Lagrange, 1736 to 1813, took mathematics into a new dimension. In his Mechanica Analytic of 1788, he formulated the entire mechanics in formulas and equations without the need for geometric representations. In doing so, he made mathematics the universal language of physics. The Lagrangian equations are still the standard tool in mechanics, astronomy, and modern fields such as quantum physics. Lagrange also made decisive contributions in number theory. He proved the theorem that every positive integer can be represented as the sum of 4 squares, a problem that had already occupied Fermat. He also developed methods for chain fractions and calculus of variations, which later became of great importance for optimization and modern analysis. The 18th century was also a time when mathematics was internationally networked. Academies in Paris, Berlin, St. Petersburg, and London exchanged ideas, and mathematicians were in active correspondence. Euler wrote hundreds of letters to colleagues, students, and even kings explaining mathematical concepts. Mathematics became a European science that reached beyond political borders. The combination of mathematics and philosophy also played an important role. The Enlightenment was shaped by the belief that the world could be explained rationally, and mathematics provided the model for this. Whether in mechanics, astronomy, or statistics, everywhere it became apparent that order and regularity prevailed, which could be grasped by mathematical means. There have also been significant advances in probability theory. Mathematicians such as Jacob Bernoulli had laid the foundations, and in the 18th century, Euler and others developed these ideas further. They were applied to games, insurance, and population statistics. This gave mathematics a new social dimension. It helped to calculate risks and to base political decisions on numbers. In summary, the mathematics of the Enlightenment was characterized by 3 major movements: the systematization of existing knowledge, the application to a variety of new problems, and the internationalization of science. Euler, D'Alembert, and Lagrange are symbols of this development. They made mathematics the universal language of reason and created tools that are still indispensable today.
Chapter 16. The Austerity of the 19th Century. Cauchy, Gauss, and Riemann. The 19th century marked a decisive turning point in the history of mathematics. While the 18th century was mainly characterized by the application and expansion of analysis, the foundations of these methods began to be critically examined. Mathematics became stricter, more abstract, and more universal. New fields emerged, old disciplines were given a firm foundation, and thought was permeated by a hitherto unknown severity. Names such as Augustin Louis Cauchy, Carl Friedrich Gauss, and Bernhard Riemann are exemplary for this era. Augustin Louis Cauchy, 1789 to 1857, is considered the founder of rigorous analysis. While Newton and Leibniz operated with infinitely small quantities, which were often understood rather intuitively, Cauchy demanded exact definitions. He introduced the concept of the limit value precisely and rebuilt differential and integral calculus on it. He also defined the continuity of a function, that there is a corresponding control of the function values for every small interval. With these ideas, Cauchy created a foundation that finally put analysis on a secure footing. In addition, Cauchy was a pioneer in function theory. He developed the theory of complex functions and proved fundamental theorems such as Cauchy's integral theorem, which is still a cornerstone of complex analysis today. His work shows how an initially vague idea became an exact science. Mathematics was no longer just intuition, but strict logic. At the same time, one of the greatest mathematicians of all time was working in Germany, Carl Friedrich Gauss, 1777 to 1855. Even in his youth, he made groundbreaking discoveries, such as the fundamental theorem of algebra, which states that every non-constant polynomial equation has at least one complex zero. In his Disquisitiones Arithmeticae, he laid the foundation for modern number theory. Topics such as congruences, quadratic remainders, and the structure of integers were dealt with systematically. To this day, this work is considered one of the most influential books in mathematics. However, Gauss was not only a number theorist. In geodesy, he developed methods for measuring the Earth, and in astronomy, he calculated the orbit of the asteroid Ceres using least squares, a method he developed himself. In analysis, he made important contributions to the theory of series and probability theory. His versatility was enormous, and he was often referred to as the Prince of Mathematicians.
Gauss's work on geometry was particularly influential. He developed the theory of curved surfaces and showed that curvature is an intrinsic property of a surface that can be measured regardless of its embedding in space. This insight was revolutionary, as it paved the way for non-Euclidean geometry. This is where Bernhard Riemann, 1826 to 1866, one of his spiritual successors, comes in. Riemann developed Riemann's geometry, which describes not only Euclidean but also curved spaces. In his famous habilitation lecture of 1854, he presented the idea of a multi-dimensional space, a concept that seemed like pure speculation at the time, but later became the basis of Einstein's theory of relativity. Riemann's geometry was the key to understanding space and time in modern physics. Riemann also shaped the foundations in analysis. He developed the Riemann integral definition, which provided a precise method for integrating functions. He also dealt with the distribution of prime numbers. The Riemann conjecture formulated by him, which makes a statement about the zeros of the zeta function, is still one of the biggest unsolved problems in mathematics today. However, the 19th century was not only characterized by individuals, but by a general movement toward abstraction and austerity. In many areas, axioms have been formulated, evidence has been tightened, and new structures have been discovered. In algebra, this led to the development of group theory, which initially emerged from the study of equations but later became a universal language for symmetries. In logic, thinkers like Boole began to put the basics of logical reasoning into mathematical form, an anticipation of computer science. Number theory also became the queen of mathematics, as Gauss called it. Researchers such as Dirichlet, Kummer, and Kronecker expanded the field, developed new number systems, and investigated the structure of integers. This seemingly purely theoretical discipline would form the basis of modern cryptography centuries later. Another characteristic of the 19th century was the internationalization of mathematics. Academies, journals, and congresses were created to promote exchange. Mathematics became a global science that was no longer practiced only in individual centers, but in an international network of researchers. In summary, the 19th century transformed mathematics from a science of intuition to a science of rigor. Cauchy laid the foundation of rigorous analysis. Gauss combined number theory, geometry, and astronomy at the highest level, and Riemann opened up new dimensions of thought that had an impact far beyond mathematics. This epoch laid the foundations for modern mathematics as we know it today, abstract, rigorous, universal, and irreplaceable for understanding the world.
Chapter 17. The Birth of Modern Algebra, Galois, Cayley, and the Structure of Symmetries. In the 19th century, algebra changed fundamentally. While in the Renaissance and early modern period it was primarily the art of solving equations, it now developed into a science that investigated abstract structures. This transformation led to the emergence of modern algebra, in which the focus is no longer on concrete numbers, but on general laws of operations and symmetries. The works of Évariste Galois and Arthur Cayley in particular mark the beginning of this new era. The roots lie in the problem of equations. For centuries, mathematicians have tried to find general formulas to solve equations, as had been the case with quadratic, cubic, and biquadratic equations. But in the early 19th century, it became clear that there could be no such general formula for equations of the fifth degree. This was finally proven in 1824 by the Norwegian mathematician Niels Henrik Abel. This is where Évariste Galois, 1811 to 1832, came on the scene. Despite his short life, he died in a duel at the age of only 20. He revolutionized algebra. Galois developed a theory that did not look at the solutions themselves, but at the structure of the symmetries behind the equations. He realized that by studying the permutations of the roots of an equation, it was possible to determine whether it was solvable by radicals. This gave rise to the Galois theory, which is still one of the most beautiful and profound findings in mathematics today. Galois introduced the concept of the group, at least in a preliminary form.
A group is a set of objects that are linked together by an operation and follow certain rules. Groups describe symmetries, be it in equations, in geometric figures, or in physical systems. This abstraction was a radical step. Mathematics was no longer only concerned with numbers and equations, but with structures that occur universally in many areas. At the same time, the English mathematician Arthur Cayley, 1821 to 1895, worked on the systematic development of group theory. He defined groups independently of equations and showed that matrices and permutations could serve as concrete models. Cayley also contributed to the development of matrix calculus, which would later play a central role in linear algebra. His work made group theory an independent field of research that spread rapidly. Group theory proved to be a universal language for symmetries. In geometry, it could be used to describe movements such as rotations and reflections. In number theory, she helped to understand the structure of equations. It later became indispensable in physics, for example in quantum mechanics, where symmetry groups determine the properties of elementary particles. But the development of modern algebra went beyond group theory. In the 19th century, other abstract structures such as rings, solids, and vector spaces were created. These concepts made it possible to unify arithmetic and geometric ideas and to examine them in a general framework. Algebra thus became a discipline that researched structures and their relationships independent of concrete numbers. An example of this abstraction is linear algebra, which developed from the study of systems of equations. Matrices and determinants, originally tools for calculation, became objects of their own studies. They formed the basis for the theory of vector spaces, which played a central role in mathematics, physics, and computer science in the 20th century. The work of Galois and Cayley also marked a philosophical shift. Mathematics was no longer just the science of number and size, as it was traditionally called, but the science of structures and relations. This shift opened the door to new worlds: abstract algebra, topology, functional analysis. All these disciplines developed from the idea that it is not the objects themselves that matter, but the relationships between them. The tragedy of Galois' life gave his discovery an almost mythical dimension. The night before his duel, he wrote down his ideas, which were later taken up and systematized by other mathematicians. It wasn't until decades after his death that the full extent of his findings was realized. Today, he is considered one of the greatest geniuses of mathematics, whose short but brilliant works set the course for modern algebra. Cayley, on the other hand, experienced the recognition of his work. He was a co-founder of the London Mathematical Society and had a decisive influence on the mathematical culture of the 19th century. While Galois opened the theory with visionary ideas, Cayley was the one who steered and systematized it. The birth of modern algebra in the 19th century shows how profoundly mathematics can change. The search for formulas for equations turned into research into symmetries and structures. Concrete calculations became abstract thinking. And a discipline that had long served as a tool for other sciences became an autonomous science that developed its own principles and yet remained universally applicable.
Chapter 18: The Emergence of Probability Theory and Statistics. Mathematics in the 19th century was characterized not only by rigor and abstraction, but also by a growing interest in phenomena of chance and uncertainty. While algebra and analysis investigated exact structures, probability theory and statistics were a branch of mathematics dedicated to unpredictability. This step was of enormous significance as it laid the foundation for modern applications in the natural sciences, economics, social sciences, and technology. The roots of probability theory go back to the 17th century, when Blaise Pascal and Pierre de Fermat dealt with problems of gambling. From the question of how to divide stakes fairly if a game is abandoned prematurely, they developed the first systematic methods for calculating probabilities. This was soon followed by Christian Huygens, who wrote the first textbook on probability in 1657. In the 18th century, mathematicians such as Jacob Bernoulli deepened the topic. In his Ars Conjectandi, 1713, he formulated the law of large numbers, which states that the relative frequencies approximate the true probability as the number of attempts increases. This gave probability theory a solid foundation and could be applied to other areas beyond gambling. Pierre-Simon Laplace also played a central role. In his Théorie analytique des probabilités, 1812, he developed a comprehensive theory that linked probabilities to analysis. Laplace saw the world as deterministic, but he recognized that uncertainty is omnipresent in the human mind. For him, probability was the measure of our ignorance. With this view, he made it a universal tool for science and everyday life. In the 19th century, probability theory was further refined. In particular, the normal distribution, described by Carl Friedrich Gauss, became of central importance. Gauss developed them in connection with measurement errors. If you have many independent influences on a result, they add up to a bell curve, the famous Gaussian bell. This finding made the normal distribution the standard model for random variables in science and statistics. Statistics initially developed out of practical needs. States wanted to count populations, raise taxes, and organize armies. Censuses were already carried out in the 18th century, but in the 19th century, statistics gained importance as an independent discipline. Data began not only to be collected, but also systematically evaluated and mathematically interpreted. A key example is the life table, which indicates how many people are expected to be alive at a certain age. Such boards were indispensable for insurance, which spread widely in the 19th century. Actuarial mathematics thus became an important field of application of probability theory. The social sciences also discovered statistics. The Belgian astronomer and mathematician Adolphe Quetelet coined the term average person. He studied body sizes, birth rates, and crime, and found that amazing regularities occur in large quantities. Quetelet was convinced that social phenomena follow the same mathematical laws as natural phenomena. His ideas shaped the emerging sociology and laid the foundation for modern empirical research. The connection between probability and statistics was also evident in biology. Francis Galton, a cousin of Darwin, studied heredity and coined the term regression. He realized that extreme characteristics, such as particularly tall height, were usually closer to average in the next generation. Galton developed charts and correlation methods that form the basis of modern statistics. Probability theory was also increasingly formalized in the 19th century. Mathematicians such as Simeon Denis Poisson and Andrei Markov introduced new models. Poisson described the Poisson distribution, which is named after him, which models rare events such as the number of accidents or error messages. Markov developed the theory of Markov chains, in which the future depends only on the present state, but not on the past. These models were later widely used in physics, computer science, and economics. The growing importance of probability and statistics reflected the spirit of the 19th century. While in analysis and algebra the search for absolute rigor was pursued, here uncertainty was accepted as part of reality. Mathematics became not only the language of certainty, but also the language of chance. At the same time, boundaries and philosophical debates became apparent. Some continued to regard probability as a mere auxiliary science. Others saw it as the key to understanding complex systems. It was not until the 20th century that probability theory was to be given an axiomatic basis by Kolmogorov. But the ground was already prepared in the 19th century. Laplace, Gauss, Quetelet, and Galton created a framework in which probability and statistics were transformed from the theory of gambling into universal tools. This opened mathematics to areas that had previously hardly been considered mathematical: society, economics, biology. Dice and cards had become a science that made the unpredictable calculable. Chapter 19. Mathematics in the 20th Century. Abstraction, Formalization, and Applications. The 20th century brought mathematics into a new dimension. Never before has it been so diverse, so abstract, and at the same time so application-oriented. On the one hand, mathematicians strove to put their discipline on a firm foundation and to rigorously define all terms. On the other hand, mathematics experienced an unprecedented expansion into the natural sciences, technology, computer science, and economics. Between abstraction and application, between philosophy and practice, a century full of revolution spanned. One of the most important currents was the formalization of mathematics. As early as the 19th century, axioms and structures had begun to be placed at the center. In the 20th century, this led to a systematic program. At the International Congress of Mathematicians in Paris in 1900, David Hilbert formulated 23 famous problems that were to shape the further path of mathematics. His goal was to establish the whole of mathematics in a system of axioms free of contradictions. However, this program was soon put to the test. In 1931, Kurt Gödel showed with his incompleteness theorems that in every sufficiently powerful formal system there are statements that are neither provable nor refutable. This shattered the dream of complete mathematics. Instead of providing absolute certainty, Gödel revealed that every theory has fundamental limits. This shock deeply shaped the philosophy of mathematics and put the relationship between truth and proof in a new light. At the same time, set theory, which had been founded by George Cantor in the late 19th century, continued to develop. Cantor's theory of infinity became the basis of modern mathematics in the 20th century. It made it possible to talk about different sizes of infinities and to systematically grasp the structure of mathematical objects. At the same time, it led to paradoxes that were diffused by the axiomatic set theory of Zermelo and Franco. Another central field was abstract algebra. The concepts of groups, rings, and bodies that had emerged in the 19th century were now systematically explored. Algebra became the language of symmetry and structure. Especially in connection with topology and geometry, completely new areas emerged. Algebraic topology studied spaces using algebraic invariants, while algebraic geometry combined algebraic equations with geometric structures. Analysis also evolved. With the theory of measure and the integration according to Lebesgue, it received a new foundation that went far beyond the classical Riemann integration. Functional analysis emerged as a theory of infinite spaces that became indispensable in quantum mechanics and differential equation theory. Mathematicians such as Banach, Hilbert, and von Neumann shaped these new approaches. At the same time, a completely new discipline emerged: computer science. Alan Turing, Alonzo Church, and others laid the foundations of computability theory in the 1930s. Turing designed a model of the abstract machine that still forms the basis of computer science today. Questions such as which problems can be solved algorithmically, or how efficient are certain methods, have become core questions of modern mathematics. With the development of real computers after the Second World War, this theory took on unimagined practical relevance. Probability theory was also re-established in the 20th century. In 1933, Andrei Kolmogorov formulated an axiomatic theory that defined probability as a measure on an event space. In doing so, it went from being an intuitive study of chance to a precise mathematical discipline. This formalization enabled applications in statistics, physics, biology, and economics. The applications of mathematics in the 20th century were manifold. In physics, it formed the basis for the theory of relativity and quantum mechanics. Einstein's general theory of relativity was based directly on Riemann's geometry, while quantum mechanics would be unthinkable without functional analysis and linear algebra. In technology, mathematics made it possible to build computers, airplanes, and modern communication systems. In business, it became the basis of game theory, financial mathematics, and optimization. Applied mathematics also developed strongly. Differential equations, numerical methods, and simulations became indispensable tools. With the increasing computing power of computers, new methods emerged that solved problems that were previously inaccessible. Numerical mathematics and algorithmic thinking came to the fore. Another major movement was the emergence of new disciplines, such as category theory. It was developed by Samuel Eilenberg and Saunders MacLean and provided a new language for expressing relationships between mathematical structures. Categories made it possible to connect seemingly distant areas and to look at mathematics on a meta level. The 20th century also brought a strong specialization. While mathematicians used to be equally proficient in several disciplines, a large number of highly specialized fields now emerged. At the same time, however, the need for interdisciplinarity also grew as many problems lay at the interfaces, for example, between mathematics, physics, computer science, or biology. Last but not least, the 20th century was also shaped by the social role of mathematics. It became a central instrument for war and peace, for industry and research. From the Enigma code in World War II to the atomic bomb to space travel, mathematics played a key role. At the same time, it became the engine of globalization by shaping communication, financial systems, and technology. In summary, the 20th century was a time of abstraction, formalization, and applications for mathematics. On the one hand, it brought unprecedented depth to basic research, and on the other hand, an explosion of practical applications. Mathematics became more universal than ever, a science that was indispensable both in the abstract heights of logic and in the concrete depths of technology.
Chapter 20. Mathematics in the 21st Century. Big Data, AI, and Open Questions. The 21st century marks a new phase in the history of mathematics. While the 20th century was characterized by abstraction, formalization, and the close connection to physics, mathematics today is increasingly determined by the challenges of a digitized world. Topics such as big data, artificial intelligence, cryptography, and quantum computing are at the center. At the same time, there are still fundamental unsolved questions that show that mathematics is never finished, but is constantly evolving. One of the biggest changes concerns the flood of data created by the internet, social networks, and sensors. Billions of data points are generated every day, and analyzing them requires new mathematical methods. Statistics play a central role here, expanded by machine learning methods. Linear algebra, analysis, and probability theory are the tools that make it possible to recognize patterns in gigantic amounts of data. Algorithms of optimization and numerics ensure that these methods work efficiently. A closely related field is artificial intelligence, AI. Behind neural networks, deep learning, and language models are complex mathematical structures. Linear algebra provides the basis for matrix operations, analysis for gradient methods, probability theory for uncertainties in predictions. AI impressively shows how mathematics works in practice. From speech recognition to image processing to medicine, modern applications are based on mathematical methods. Cryptography also remains a central topic. In the digital age, communication, banking transactions, and personal data must be protected. The methods used today are often based on number theory, especially on the difficulty of factoring large prime numbers or calculating discrete logarithms. But the development of quantum computers calls these methods into question. Quantum computers would be able to solve many of these problems efficiently, which is why intensive research is being carried out on new cryptographic methods that are also secure in a quantum world, so-called post-quantum cryptography. At the same time, quantum computing opens up completely new perspectives. She combines mathematics with quantum physics and develops models that work beyond classical logic. Linear algebra, Hilbert spaces, and probability theory play a fundamental role in this. The question of which problems quantum computers can actually solve faster than classical computers is one of the most exciting challenges of our time. Applications in the natural sciences also remain a driver of mathematical development. In physics, for example, mathematical models are indispensable for the exploration of the universe, from cosmology to particle physics. In biology, differential equations and network theories help to understand complex systems such as ecosystems or the human brain. In medicine, mathematical models are used to simulate the spread of diseases and optimize therapies, a topic that was particularly important during the COVID-19 pandemic. In addition to the applications, mathematics also remains alive in its pure form. Many of the major unsolved problems are still open. Riemann's conjecture, one of the most famous problems in number theory, is still waiting to be proven. Equally unsolved are questions such as the PNP problem, which decides whether all problems whose solutions can be efficiently tested can also be solved efficiently. These questions are at the heart of the so-called Millennium Problems, formulated by the Clay Mathematics Institute in 2000. Each proof is endowed with a prize of $1 million, but their real significance lies far beyond that. They show that mathematics remains full of mysteries despite all the progress. Another field that has grown strongly in the 21st century is interdisciplinary mathematics. Today, problems often arise at the interfaces of different disciplines. Financial mathematics models complex markets, bioinformatics decodes the genome using combinatorial and statistical methods, and network theory examines structures ranging from the internet to social systems. Mathematics becomes a universal tool that can be used wherever structures, patterns, and dynamics occur. Mathematical visualization and simulation have also reached new dimensions through modern computers. Today, fractals, chaos theory, and dynamical systems can not only be studied theoretically, but also visualized. This gives mathematics an aesthetic component that at the same time enables insights that were previously hidden. In the 21st century, mathematics is thus more than ever both an abstract science and a practical key technology. It combines the highest levels of theory, such as topology or number theory, with the most pressing problems in practice, from climate models to secure communication. It is universal, flexible, and indispensable. The image of mathematics has also changed as a result. It is no longer just the silent language of scholars, but visible in our everyday lives, in search engines, in navigation systems, in medical diagnostics, in financial transactions. Behind every app, every algorithm, every technical device is mathematical thinking. At the same time, mathematics remains a deeply human activity. It thrives on creativity, intuition, and the search for truth. Even though computers do a lot of calculations today, it is people who develop the ideas, recognize the structures, and ask the questions. The mathematics of the 21st century shows that abstract thinking and practical applications are not opposites, but two sides of the same coin. This closes the arc from the first counting stones of the Stone Age to the algorithms of artificial intelligence. Mathematics has always been the art of recognizing patterns and bringing order into the world. In the 21st century, it remains that art, only on a stage that is more global, complex, and dynamic than ever before.